So in these videos, we're gonna cover the higher order ODEs, and we're gonna be looking at non-homogeneous equations, and we're gonna be solving them through the method of undetermined coefficients, which we have already done in previous videos. You can go back and watch this, and you can also go back and watch the videos for higher orders that we just did, so that you guys can catch up and then understand whatever we're doing. So let's get right away into this problem. So for this one, you can see we have y to the fourth derivative. Usually they're derivatives, so we have to write the 4 primes. We just write them like the Roman numerals. This y to the fourth derivative minus 16y equals to sine of x. So let's solve this one. So our characteristic equation here, we have lambda to the fourth minus 16 equals to 0. And this one, basically all we need to do is send the 16 to the other side. So lambda to the fourth is equals to 16. And all right, so what do you think we should do? So we are going to take the square root. So we have lambda to the fourth. We take the square root of 16. And what are we going to get here? Well, square root of lambda to the fourth, that's, I'm just going to use a different color here. So that will be lambda squared, and that equals to the square root of 16. Don't forget, it's a plus or minus 4. Okay, now let's continue taking the square roots here. So we have 2 roots, we still need a little more. So when we take the square root again, square root now of lambda squared, we're gonna be taking the square root of plus and minus 4. So do not forget everything we're gonna get here. So we can split up into 2. So basically, when we do that, it's like if we're doing the following. We're doing, we have 1 lambda that will be equals to the square root of positive 4. And the result for this will be plus and minus 2. So that's a pair of lambdas here. This is another pair of lambda, plus or minus 2. And then we have the other lambda that's taking the square root of negative 4. And what do we get here? This lambda is equal to plus or minus 2i. So you can see these are our 4 roots. So you can write here that we have 4 roots. And what are those 4 roots? Well, we have negative 2, we have positive 2, we have negative 2i and positive 2i. That we know that these ones, they're a case 3, while this one are a case 1. So make sure, it's really important you guys do this. It's a pretty common mistake that I see, that everybody just takes like, oh, 16 square root, that's a 4, but they forget the plus or minus. And then when they take the square root, they just get like, oh, plus or minus 2, but don't forget, you're taking the square root of plus and minus 4. So there's already 2 roots. So you get to take the square root of the positive 4, which we get plus or minus 2, and the square root of the negative 4, which should be plus or minus 2i, which will give us our 2 cases. So it's pretty important that you guys remember that. So based on this, my solution here, my homogeneous solution, right? This is my homogeneous. I forgot to write it here, so I'm gonna write it. So this is for my homogeneous, where we have y to the 4 minus 16 equals to 0. All right, so for this one, my homogeneous solution, y of h, it's equals to c1e to the negative 2x plus c2e to the 2x plus c3, and this will be cosine of 2x plus C4 sine of 2x. And this is my homogeneous solution. There we go. So that's what we have for the homogeneous. And now you can see we have our four roots, our four solutions, the exponentials and the cosines, because they're pure imaginary. We don't need to multiply them to an exponential. And now let's find our non-homogeneous. So I'm right here for the non-homogeneous. And for this one, we need to see our R of x. For this case, R of x is equal to sine of x. And we need to also check that it is not present in our homogeneous. So it's cosine of 2x, the same thing as sine of x. No, it's not. And then we have its sine of 2x, the same thing as sine of x. No, it's not. Therefore, we don't need to do any modifications, and we can use basic rule. So using basic rule, I'm gonna paste my table here to select my YP. So according to this, my corresponding YP, all right, so YP, it's equals to K cosine of x plus M sine of x. And remember, when we did this, we need to apply this into our original equation. So I need to find all the way up to YP fourth derivative. So let's find each one of those. So this one will be YP prime. So I'm gonna get negative K sine of x plus M cosine of x. Good thing that this one, we don't need to multiply it into any other number inside the signs. If not, we would have already doing a big chain rule. Okay, YP double prime, then we get negative K cosine of x minus M sine of x, YP triple prime, we get K sine of x minus M cosine of x, and then YP to the fourth, we get K cosine of x plus M sine of x. So we plug this into our original equation. So YP to the fourth minus 16 YP, that equals to sine of x. So plugging in everything together, we're gonna get here K cosine of x plus M sine of x minus 16 times YP, which should be 16K cosine of x minus 16 M sine of x, and this is equal to sine of x. You can see that if we get everything together, this will transform into negative 15K cosine of x minus 15M sine of x equals to sine of x. So if we do this in the two different parts, so one for cosine and then one for sine, you can see that my terms that have a cosine of x, I will be negative 15K. I don't have any other cosines on the other side, so it's equal to 0. So we get that K is equal to 0 for this one. So let's do it for the sine. So for terms that have a sine of x, I have negative 15M, and on the other side, I have 1 sine. So solving from here, we get that M is equals to negative 1 over 15. So I can plug that in back into my YP. So then YP is equals to negative 1 over 15 sine of x. And then my general solution for this will be putting them together. So y of x is equals to C1. Well, I don't think it's going to fit here on top. So I'm just going to write everything at the bottom. So y of x is equals to C1 e to the negative 2x plus C2 e to the 2x plus C3 cosine of 2x plus C4 sine of 2x minus 1 over 15 sine of x. And everything here in blue will be my general solution. So you can see this problem is pretty straightforward. We have done something like this. Maybe we're just adding a couple more steps, but other than that, there's no difficulty in solving this one. It's same things we've been doing in the previous videos. So let's do one more problem. Hopefully you guys will get it this time. Okay, so in this problem, we have y triple prime plus ya double prime, plus ay double prime plus 15y prime equals to e to the 3x. So solving this one, once again, we start with the homogeneous. So we start with the homogeneous, and for this one, we're gonna get y triple prime plus 8y double prime plus 15y prime is equals to 0. And after this, we do our characteristic equation, which for this one will be lambda cubed plus 8 lambda squared plus 15 lambda equals to 0. So we can factor out one of the lambdas. So we can have here then lambda squared plus 8 lambda plus 15 equals to, let me just rewrite the 15, equals to 0. So from here, then we can continue working with that. So we have lambda times, we can factor this out like this. So it will be lambda and lambda, something that gives me 8 and 15. So that's positive 3 and positive 5, right? 3 times 5, 15, 3 plus 5, 8. And therefore, from here, I get then my roots to be lambda 1 equals to 0. And then we have lambda 2 equals to negative 3. And lambda 3 equals to negative 5. So you can see, once again, for this one, all we got were a case 1, because all of them are 3 different roots, 3 different numbers. So with this one, all I need to do is write my homogeneous solution. So this is C1 because the lambda 0. So there's the exponential basically cancels, plus C2 e to the negative 3x plus C3 e to the negative 5x. And this is my homogeneous solution for this problem. Now, once again, I need to solve for the non-homogeneous. So I want R of x for this one, it's e to the 3x. Let's just check that we don't have that before. So e to the negative 3x, it's not the same thing as e to the x, to 3x. And e to the negative 5x is not the same thing as e to the 3x. Nor is the C1, which is just a constant here. So we can use basic rule. All right, and we can use our table. So let me paste it here. And with this, then it means that our yp corresponding will be k e to the 3x. Once again, I need to find all the others. So this will be yp prime. I'm going to get 3k e to the 3x. Yp double prime will be 9k e to the 3x. And then yp triple prime will be 27k e to the 3x, correct? All right, so let's plug into our original equation, which is yp triple prime plus 8yp double prime plus 15yp prime equals to e to the 3x. So substituting all the values, we are going to get here 27k e to the 3x plus 8 times 9 k e to the 3x plus 15 times 3k e to the 3x equals e to the 3x. Okay, so after we put everything together here, we're gonna write it. And this will be 27k e to the 3x plus 72k e to the 3x plus 45k e to the 3x equals e to the 3x. So we can simplify this. 27 plus 72 plus 44 plus 45, that's 144k e to the 3x, and that equals to e to the 3x. So then if we solve for k, we can cancel out this and this, and we're gonna have here then that 144k is equals to 1. So k is equals to 1 over 144. Therefore, I have then that yp, it's 1 over 144 e to the 3x. And this is my non-homogeneous solution. And then my final solution, when I write it here, I will have C1 plus C2 e to the negative 3x plus C3 e to the negative 5x plus 1 over 144 e to the 3x. And this in blue will be my general solution. So once again, this was a higher order problems in non-homogeneous ODEs. You might find similar problems later on. But you can see they're pretty straightforward. If you know how to solve this one from the previous chapters, how to solve it for a second order, then you can definitely solve this one for any higher order. So that's it for this time. I'll see you in the next video. And as always, good luck.